My talk is about more or less the similar subject. It's again delamination, buckling of coating from substrate. Here are examples from literature. I will refer similar groups of researchers as Harvard group and Grenoble group who studied this subject. But I will talk from a little bit different point of view, more theoretical, more particular one point. Here is the motivation, what was talked about in previous report. So it's in microelectronics, in optics, in biology, everywhere there are coating and substrates, and due to prevent cracking of substrate, usually it works under pre-stressed compression, and this may cause buckling and delamination, and that's why we need to use a balance between what pre-stress can be applied so to prevent buckling. So I will talk about buckling and delamination. Here, a very brief review of researchers who work on the subject. And usually the layer, due to difference between its length and thickness, it's very attractive to use beam, plate, or shell theory to describe it, as was shown. But the problem is that if we use plate or shell, if it's called theory, we need to apply some boundary condition. And this boundary condition, as we discussed before, it's something in between pure clamping, rigid clamping, and just simple support. Here are solutions. Actually, it's a Euler solution for buckling stress. If it's rigid clamp. But it's not the case. If the substrate is compliant, there is always, when we consider this as a plate, there is always initial displacement in both directions and initial angle of rotation due to compliance of substrate. Even if the substrate is absolutely rigid due to softness of the coating, it still exists. So for rigid compliance, this part should be rigid also. But it's small, but still exists. So the point is to find this initial displacement in both directions and angle of rotation in terms of acting stress parameters, force and moments, so-called matrix of elastic clamping or compliance, matrix of compliance here. First of all, will be introduced in this works for these three parameters relate with three force parameters of beam or plate theory by 3x3 matrix in general. 2x2 matrix was introduced, I think. This work here it was calculated numerically. Here it's a fine element. Here numerical solution of integral equation. Here we found for one particular coefficient for a particular case asymptotic solution. And now I will try to show how it's possible to derive this matrix of elastic compliance for particular cases, exact solution, but for other cases, just approximate solution, analytical solution. Here, the same can be done if it's not infinite, substrate is not infinite, but also of finite thickness. There is still different non-zero displacement and non-zero initial angle of rotation of the individual. So here the list of obtained solutions. The exact solution was obtained for two particular cases. Strip on half plane with vanishing parameters of elastic mismatch, and two strips of equal thickness with vanishing mismatch parameter. All the rest was obtained approximately. Numerical formulation, I think that I can very brief, just to solve elastic problem with a layer and another layer with different properties, or half plane with obvious equation of elasticity and boundary conditions. So the problem is by applying Laplace transformation reduced to matrix Riemann-Hilbert problem, which is solved by Wiener-Hopf technique. It's rather awkward, but still can be done for exactly for these two particular cases. For the rest, it was done with neglecting some terms. Here is the method I will drop, and here is the finite solution when we obtain this matrix of elastic compliance somewhere with this delta is just awkward expression of integral. So but they are well converged and calculated, and it's maybe approximated by a simple formula. It's a ratio of elastic modulus, so it's 1/3. So this is all the parameters are very simple. Also, despite of these awkward calculations, the final results are rather simple. Here is the similar condition for two strips, and here propagation, when we use this for elastic clump plate and apply the obtained boundary condition. So, for example, the problem for finding critical stress reduced to this simple eigen value problem, which is governed by the single parameter. So the ratio between Euler critical stress and the real one is governed by a single parameter, which is a ratio of thickness to length and square cubic root of elastic modulus. And it's supported by numerical results, so there is a single mastic curve for such a problem. And even for here some asymptotics for not for long and rather rigid substrate, it's just can be expressed in series, so it's just an elementary solution. So what we can obtain as a result? As a result, we first I want to say that in these problems, not only such things as stress intensity factor is of interest. Of course, they were obtained, but it's everybody obtained. But I want to say that this matrix of elastic compliance, coefficient of this matrix, could be also of interest for these kinds of problems. And by using this, if we obtain them, in our case, some of them were obtained exact analytical solutions. So applying them to problems of plates and shells, we can got simple and convenient for use solutions. That's what I wanted to say. Thank you.